Hello guys, and welcome to another calculus video. Today we're going to be checking out this amazing integral, the integral from 0 to infinity of sine squared of x over x hyperbolic sine of x dx. It's really cool, mostly honestly because of the cool result that we get, which is, as you can see, I've shown it right here. I just love the way that it reorganizes itself into this awesome expression. And I really enjoy all the methods that I use to evaluate this integral. So without any further ado, let's go ahead and evaluate it. First thing I want to note is that we will be using a result that I derived in a previous video, which is that the integral from 0 to infinity of sine of ax over sine h of x dx is equal to pi over 2 times hyperbolic tangent of pi over 2, or of a times pi over 2, sorry. So let's go ahead and evaluate the integral. So we're going to use my new most number one favorite trick in the whole wide world, which is the conversion of sine squared of x into an integral. So what I mean by this is sine squared of x, I've just replaced it with 1 minus cosine of 2x all over 2, just using our trig identities. And now we're going to do my new most favorite trick, and we are going to write this as 1/2 integral from 0 to infinity of negative cosine, or actually I can just write this as cosine, I guess, cosine of theta evaluated at theta equals 0 and theta equals 2x. Then, of course, we have to still have x sin hx on the bottom, dx. Then we will convert this into an integral. So we still have our 1/2 integral from 0 to infinity. And then now we're going to write this as the integral from 2x to 0 of the derivative with respect to theta of cosine theta, which is negative sine theta, d theta. Then I'm just going to go ahead and use this minus sign to flip the bounds here. And then we're still over x sin hx dx. Next, we're going to substitute 2xu is equal to theta on the inner integral. So that means that d theta is equal to 2x du. And we can go ahead and substitute that in. You can see that when we're going to end up with the integral from 0 to 1, because when u equals 1, that's when theta equals 2x. And then sine of 2xu. And then instead of du, we have 2x du. And we have this 1/2 outside, and this x, and then sine hx. Now on this inner integral, we can go ahead and bring all these constants outside, which means we can cancel this 2 with this 1/2. And this x can also come outside because u is our variable integration here, so x is really constant with respect to u, so that means we can go ahead and cancel this as well. So we'll end up with the integral from 0 to infinity. And now I'm going to go ahead and bring sine h of x inside the first integral because, again, sine hx is constant with respect to u. So that's the integral from 0 to 1 of sine of 2xu over sine hx. And then we're going to have du dx. Then we're going to apply Fubini's theorem and interchange these integrals. Now I don't have a justification for this, but we're just going to interchange the bounds and hope that it works out. So now, having flipped the order of integration, we can go ahead and apply our formula. So I'm going to go ahead and make some more space. So now all we have to do is evaluate this integral, which we can use the formula that we proved in another video, which I will link, to evaluate this integral. So we'll just end up with the integral from 0 to 1 of pi over 2 inverse hyperbolic tangent of, in this case, our a is the coefficient of, or sorry, I should reorganize this, I suppose. It would be 2ux. Our a is just the coefficient of x, which is 2u. So we're going to have 2u pi over 2. So we can go ahead and just get rid of these. And we just have u pi. And then we just have our du, right? Then we can bring this pi over 2 to the outside. Or actually, I'm going to bring the 1/2 to the outside, and I'm going to leave the pi inside. And the reason for that is we're going to substitute u pi equals v. And that means that pi du equals dv, and we have pi du right here. So I'll end up with 1/2 the integral from 0 to pi of tan h of v dv. Nice. Now all we have to do is integrate tan h, which is relatively simple. Remember that hyperbolic tangent is actually just hyperbolic sine over hyperbolic cosine. And the derivative of hyperbolic cosine is hyperbolic sine. So we could write this as the integral of d cosh of x, right? And this would make our integral just ln absolute value, but we don't need absolute value because cosh is always positive. And so that's our indefinite integral. So this means we're just going to have ln cosh of x evaluated at pi and at 0. But at 0, cosh of x is just 1, and so ln that is 0. So overall, our answer is 1/2 ln cosh pi, which is also equal to ln square root of cosh pi, which I just think is an absolutely magical result. So this was a little bit of a shorter video, but I hope you guys enjoyed. I really enjoyed using the methods that I showed here in order to evaluate this really cool integral. I know some other people left in the comments of my community post on how to use the infinite product for cosine to evaluate this. I would absolutely love to see that result if anyone would like to share it with me, because I'm actually not familiar with that product or exactly how to use it. So yeah, I would really love to see that if you guys want to show that to me. And yeah, so I hope you guys enjoyed the video, and I'll see you next time.